So what we have here has the molecular formula C9H12O. Activate this. And remember our formula for unsaturation, so that's 9 minus 12 over 2 is 6 plus 1, so 9 minus 6 is 3 plus 1 is 4 unsaturations, meaning 4 rings or 4 double bonds or 2 rings and 2 double bonds or some combination of that. Now the IR happens to match one of the big 4. Notice what this is right here. OH, I hear someone say. So that's an OH stretch. The OH bond stretch, not nuclei. This IR is electrons actually, unlike NMR. And that's at 3488 reciprocal centimeters is the units of IR. So always have your units. You can just forget about all that and all that. So that's, remember the big 4, that's posted on Canvas also. So we have our formula C9H12O. We can already subtract HO. It's almost a certain OH group there. So that's now leaves us with C9H11. And I'll hit save. Oh, I'll just leave it at that. Change the name later. So we're done with the IR actually. Now in the NMR, we have in the proton NMR our counting of peaks. So 4 hydrogens, 5, 6, and 6 is 12. That matches the total number of hydrogens in the formula. So 12 hydrogens, yes. We've already found an OH, and remember that oxygen and nitrogens with hydrogen on them, the hydrogen is typically not split. So even though there could be hydrogens adjacent on an adjacent carbon, these are typically not split, meaning they're singlets. So we can go looking for the singlet that integrates for 1 hydrogen, and there it is. So that's pretty much the only one that it could be. So we've already assigned that one at 4.56, at 4.7 ppm. So ppm is units, or you could say delta 4.7. And then in the carbon NMR, all our hydrogens are accounted for. In the carbon NMR, we've got 1, 2, 3, 4, 5, 6, it's telling us. 7, 8. Is that how many carbons we have? 9. Okay, so it looks like one of the carbons is doubled up. So 8 carbon signals. 1 is therefore doubled. So you write down these little pieces of information, you file them away, but don't forget about them. Which one's probably doubled, if you had to guess? It's not certain, but. So that one's clearly much taller than the others. So likely 24 ppm. And now we've accounted basically for all our carbon peaks. We can make a little note though that we have 2 that look like quaternary. In other words, no quaternary carbons, no hydrogens attached. So double bonded most likely. Now, anything obvious, quote unquote, in the proton NMR? So among the more obvious things are methyl groups, and it does look like we have 6 hydrogens in the methyl chemical shift region, typical region of the chemical shift. And so that would be two methyls, so it does look like we have two methyl groups. Pretty obvious. What about benzene type rings? 7 to 8 ppm. Yes, it certainly does seem like we have 4 hydrogens on an aromatic ring. And that would necessitate that we have 6 aromatic carbons, right? So do we have 6 aromatic carbons in the aromatic carbon region, which is basically like here, stretching to there? 1, 2, 3, 4, 5, 6. So that's certainly those two looks at the aromatic regions totally agree with each other, right? So as you get more and more agreement, you get more and more confidence. So now this is going to make our what's left a lot more manageable. So we had C9H11. Subtract 2 methyls, so that's C2H6. Leaves 6, 7, 8, 9, 10, 11. It's H5, C7, and then we can also subtract C6H4 for this piece. Look at that, C6H4. There's only CH left. Okay, so we've got our 4 aromatic hydrogens exploded up here, expanded up here, I should say. There's the OH, there's the methyls. Here's the only signal unexplained. It's highly split, and we know it integrates for 1 hydrogen, so there's our CH. There's our remaining CH. Having done a bunch of practice problems, we would maybe recognize a pattern of signals, not just a single signal, but the combination of these two. So looking at the splitting is usually the way you're going to have to solve the final, get the final answer. So 1, 2, 3, 4, 5, 6, 7, if that reads correctly, a septet. And from our experience working, lesser problems like in the book reading and other practice problems, how do you get a CH to be split? Remember, this is going to give you 1 initial signal. How do you get that to be split an additional 6 times, resulting in 7 lines total? Well, it's not going to be attached to the ring. It's not going to be the ring hydrogens that can do that. They're all scattered, right? It's got to be the only other hydrogens present, the 6, exactly 6, methyl hydrogens, splitting that signal into a septet. And now we've got this piece, which we recognize as an isopropyl group from way back in the dim and distant past of the second week. We have accounted for our remaining atoms. We've got nothing left. So we've got this piece. We've got an aromatic ring with 4 hydrogens around it, and we've seen this before too. So we've seen the 4 possibilities where they're arranged like this is one of them. Sorry, we have our OH piece, right? And we know the OH isn't connected here because that would create and close off that molecule. That would be a small alcohol. So we know that we got the OH here and the isopropyl group there. Or, 1 minute before I'm kicked off. H, 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 H. We'll worry about. So, and then I guess you could have 3 in a line, 1 separate, OH there. So the splitting is going to reveal what's going on here. Way up here in the corner, you see this pattern of doublet, triplet, triplet, doublet. It's expanded above that. For those of you about to, or for the video ending here, the only one of these three possibilities that matches that is this one, so that is the answer.